Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Hey, step on inside and we are going to look at section 2.4 of the Integrated Math 2 Big Ideas Math textbook on solving polynomials written in factored form. Now, we're going to look at what factored form means and what it means to factor. This is but step one of a bunch of factoring that we're going to be doing moving forward. We're going to start today with finding the greatest common factor, or it'll already be factored out, but it's a nice way of showing how you solve equations that are not just linear, with just a single x in it. How do you solve one with an x squared or an x cubed or whatever? There are a lot of different ways to do it, and some aren't possible through factoring, but these ones obviously will be when it's in the section. So we'll take a look at the lecture set. We'll go over the problem set, which I believe goes up to number 48. I'll have some fun doing it. Got some giants in the background. Let's go ahead and take a look at what we got here. Section 2.4, we are going to begin by using what's called the zero product property, and I think they're going to teach it pretty well. It's in the name itself as well. We're going to factor polynomials using the greatest common factor. That's what GCF stands for. So if I ever say GCF, that's what I mean. And we're going to be using the zero product property to solve real life problems. So going back to it, of course, word problems tend to pop up in a lot of these things all the time. So just get used to it. It's okay. We'll see what they throw in along the way. Okay, using the zero product property, let's see what they want to say about this. A polynomial is in factored form when it is written as a product of factors. So here you see what's known as standard form. We've talked about that before, meaning descending order of degree, but terms separated by pluses or minuses. But this is not a product of two numbers. Here I have an x squared plus 2x. That's a sum, not a product. X squared plus 5x minus 24. Sums and differences, not products. Factored form has products. You can see here is x times x plus 2. And I know you might think, Mr. Robinson, x plus 2 is a sum right there. Yeah, but it's being multiplied by x. The entire quantity is. If x was 5, this would be 5 times, 5 plus 2, 7, right? That's a number times another number. And using the zero product property, which we'll get into what that means, but that zero product property requires a product. So factored form gives us that if we're able to factor things, which, by the way, this is the factorization of this. We'll talk about why that is. Today, we'll not talk about why this is the factorization of that. We'll get into factoring this into that later. But this is its factored form and its factored form. And if we can get it into its factored form, we have a way of solving quadratic equations. Specifically, these are quadratic equations by factoring. And so that's going to be one of the goals of today and in the future things that we do. When one side of an equation is a polynomial in factored form and the other side is 0, we use what's called the zero product property to solve the polynomial equation. Now, this isn't some fancy formula. A property is a math idea. It's a math truth. It's an idea that has logic and purpose in it, and I'm going to try and explain it if this doesn't do it in full, but it looks like they will. The solutions of a polynomial are also called roots. Okay, whenever you see the word roots, we're talking about, hey, x equals what when we solve it. So zero product property, it says this in words, in plain English. If the product of two real numbers is 0, if you multiply two things and the result is 0, then at least one of the numbers is 0. One of them has to be 0. I'll explain more of that core as to why, because it looks like they go straight into examples. Their better way of putting it is if a and b, being those real numbers, if a times b equals 0, then either a equals 0 or b equals 0. And that's important because we're going to be writing two different equations to make conditions for this in order to solve. I think you're going to make a lot of sense of this, but we have to make sure to break it down pretty well. Now keep in mind, this only works for 0. This thing's in the name, zero product. Things that multiply to become 0. And if you have a factored form set of values, like you're going to see down here, that multiply to become 0, then you can create conditions of separate equations to say either this equals 0 or that equals 0. And think about why this only works with 0. One of my numbers has to be, I can't multiply two non-zero numbers to get 0. 1 times negative 1 is not 0, right? You can't get two non-zero numbers and multiply to get 0. One of them has to be 0. And of course, 0 times 0 is 0. But the other idea of that is as long as one number is 0, then the result is 0, right? 0 times a billion is still 0. So it works with 0 that way. It doesn't work with other numbers that way, though, right? Think about the number 10. If a times b equals 10, then either a equals 10 or b equals 10? I don't think so. I can multiply two non-10 numbers to get 10. I can do 5 times 2. I can do 20 times 1/2. I can do -1 times -10. So I don't need to do that. And as long as one of the numbers is 10, then the result is 10? No, 10 times 2 is not 10. So it doesn't work with 10. It doesn't work with any number but 0. 0 is very special in that way. So keep that in mind when it comes to this property. If you're not set equal to 0, you're not solving it that way. So I don't know how they'll trick us or not trick us, but we'll take a look with some of the examples they have. So example number 1, we have parts A and B solving each equation. These are already in factored form. I have 2x times x minus 4 equals 0. 2x is a quantity, x minus 4 is a quantity. They're multiplied. I'm multiplying this by this to get 0. One of these has to be 0. So what values of x makes this true? Well, if 2x was 0, in that case, I could divide by 2 and x would be 0. And that would get me 0 as a result. If x minus 4, that's a weird arrow, if x minus 4 equaled 0, I could add 4 to both sides and x would equal 4. So x could either equal 0 or 4 in this equation, and I would get 0 out, one or the other. There's more than one solution. Not like an infinite number of solutions, but there are two of them. When you look at part B, x minus 3 times x minus 9 equals 0, the same kind of thing. If x minus 3 equals 0, you add 3 to both sides and x equals 3. If x minus 9 equals 0, you add 9 to both sides and x equals 9. Now remember, one or the other works. Plug in 3 into here, 3 minus 3 is 0, times, I mean, you can see it looks like they do it for the first example. You either plug in 0 for this, 0 times negative 4 is 0, or plug in 4 into this, 8 times 0 is still 0. Same thing happens here. Here are your roots, another way of saying solutions, and it's more than one answer in this case as well. Quadratics will tend to have 2 answers, and I think we're going to probably look at a lot of quadratics. Some more examples here, but we're going to do some when we do our problem set. Okay, moving on. When 2 or more roots of an equation are the same number, the equation has repeated roots. Great. We're going to see when we run into those. But here are a couple more examples. 2x plus 7 times 2x minus 7 equals 0. Notice either one or the other equals 0. And we're creating two conditions. You're solving these parts separately. At this point, I'm going to subtract. It looks like they skipped a step. Subtract 7 from both sides and then divide both sides by 2. And here, we add 7 both sides and divide both sides by 2. Now they're two separate equations that you solve for separately, but they are showing the two different sets of solutions for your answer. And those are two different answers. The next one says x minus 1 squared equals 0. This might be where they're talking about repeated roots. X minus 1 squared also means x minus 1 times x minus 1. If x minus 1 times x minus 1 equals 0, either x minus 1 equals 0 or x minus 1 equals 0. It sounds like the same thing twice. X equals 1 or x equals 1. What's the difference between them? Nothing as far as value goes, but they mentioned this repeated roots thing, something that really applies a lot more. I think when you hit integrated math 3, you're going to see more on how graphing polynomials and multiplicities apply. There's a real reason to talk about that. Also something called the fundamental theorem of algebra, or the rational, and now suddenly I can't remember. Fundamental theorem of algebra, I think, is going to say something big about that. That sounds important. And this third one here has 3 things multiplied. I mentioned if a times b equals 0. What about if a times b times c equals 0? Does it still work? Yeah, one number's 0, then it multiplies with everything else. It's going to wipe it all out. It all becomes 0 in the end. So, ultimately, you can have many things in factored form, and as long as they multiply together, then you can set conditions for them to equal 0. And you get x equals negative 1, and x equals 3, and x equals 2. So there's just the concept of that. That's the zero product property in a nutshell. Okay. Now, what probably goes without saying, I don't know if you noticed this. You see the x plus 1? Oh, x equals negative 1. That's an answer. X minus 3. Oh, x equals 3. It's the answer. You're just change the sign. This was because you got to find what value goes into here. Does it always work that way? No, we just saw one above that showed 2x minus 7 and 2x plus 7. Negative 7 wasn't an answer. It was negative 7 halves. You have to ask yourself what value of x would give you 0, right? That's the whole goal of this setup. There are some times where you can, like if I see x plus 1, it's because it's 1x plus 1. I'm just dividing both sides by 1 and I don't change my value. So if you ever see me go straight from here to here, hopefully you're understanding why negative 1 is the value that would give me 0 in that instance. Okay, some more examples there, but we'll go ahead and move forward and look at factoring polynomials using the greatest common factor. That's what that stands for. This time we're actually going to get into factoring, only with GCFs. Next video, we're going to get into factoring basic quadratic things, and then it gets more complex. And it will get a little complex for some of you guys out there. But let's start soft. Let's start with just finding a greatest common factor. A greatest common factor is where, let's see if they tell you, a monomial that divides evenly into each term. You want to find the largest value that can divide out. And it's not just the number. More importantly for this thing, it's the variable. And we've done things with exponential properties already to hopefully make sense of this. And you've done distribution before as well. Factoring is the opposite of distributing, which is a nice way of talking about it. So let me look at this example that we have right here. If we have 4x to the fourth plus 24x cubed, we want to come up with a factorization of this and find what the largest value is that I can divide out of both terms, or factor out, and the largest variable set that I can factor out. So 4 can divide both out of both 4 and 24. So can 2, but 4 is the greatest common factor. So we can factor a 4 out of there. But with the variables, the more important part, it is for these kinds of problems, because if we want to solve, x to the fourth and x to the third can both divide out in x to the third. They can divide out the smaller of the two, right? It's the greatest one that you can do, the smaller of the two. So we can factor out an x cubed. Factoring out is like division, but you leave the result on the outside. It's the opposite of distribution. If distribution is like multiplying, what's 4x cubed times x? Boom, 4x to the fourth. What's 4x cubed times 6? Boom, 24x cubed. So you find out what divides out, and then you write what would remain inside there that had you distributed, you would get that. So 4 divides out of 4, you get 1. X cubed divides out of x to the fourth, you get x. 4 divides out of 24 and you get 6. X cubed divides out of x cubed and you get 1. So that's why you're left with x plus 6. Let's see some more examples that they have on this and make sense of what we're doing and why. We solve equations by factoring. What does factoring ultimately do? It creates a product. And if you have an equation set equal to 0, or you have an equation that you can set equal to 0, we can create the product, use the zero product property, and be on our merry way. So on this problem, 2x squared plus 8x equals 0. Don't dare and try and combine these and get x's on the other side of the equation. That's not the goal of a problem like this. You want to factor. The greatest common factor of 2 and 8 is 2. The greatest common factor of x squared and x is x. It's the most number and variable that I can divide out of both terms. And what remains inside, 2x times x is 2x squared, 2x times 4 is 8x. Anyway, we created a product. It's set equal to 0. We can now solve this using the zero product property. See, before we couldn't solve, and there are going to be ways you're going to learn in future chapters, but you couldn't solve quadratics by get the things by itself on one side of the equation because there are multiple terms with an x in it. So there's another means of getting the x's by themselves in a great linear sense, and that's by factoring. That's what we're doing. So that's the answer there. X either equals 0 or -4 with our roots. In part B, you see 6n squared equals 15n. Don't dare and try and do things like divide both sides by n and such. You're going to be getting rid of a solution if so. We can factor it out, but we can only do it when they're on the same side of the equation. And our goal really is to use the zero product property. So set this thing equal to 0 to start with. So they say subtract 15n from both sides. Boom. And you want it in standard form. I believe that it's much easier to determine what can factor from largest to smallest, especially with your variables. So standard form is going to be the way to go. 6 and 15 can both divide by 3. N squared and n can both divide by n. So factor that out and write what remains inside. You might not be really good on this step yet, saying how do you know what to write here? Once again, it's the opposite of distribution. 3n times what is 6n squared? Well, 3 times 2 is 6, and n times n is n squared. And 3 times what is -15n? It's -5. I mean, you can say it as division, but I think most people like to see it more as multiplication. I personally do, I think. And that's how I work it out. So anyway, either 3n equals 0, divide by 3, n equals 0, or 2n minus 5 equals 0, add 5 to both sides, and divide both sides by 2, n equals 5 halves. Improper fractions are totally fine. Don't try and write it as a decimal. Definitely don't try and round it. Mixed numbers, no go. You're good. So some more problems. Like I said, we're going to be doing some of our own eventually. Okay, solving real life problems. Probably the last part of the lecture thing, since that's what they were mentioning. Modeling with mathematics. You can model the arch of a fireplace using this equation. Fantastic. Where x and y are measured in inches. The x-axis represents the floor, so we got a floor right there. Find the width of the arch at floor level. So what they're really asking us to do, this goes a little beyond maybe what was taught so far, but this is the application. So here's the floor on the x-axis, and here's the arch that makes the fireplace. They want us to find out what this distance is. to find out what this distance is, we want to find what x values these are. These are x-intercepts. They say the x-coordinates of the points where the arch meets the floor is at y equals 0. If you remember how your lines work in your values, this is y equals 10 and y equals 20 and y equals 30. Well, this is y equals 0. So they gave us an equation that says your y of your graph is modeled by this. We didn't have to draw the graph, but they're asking, hey, if you substitute 0 for y, let's solve for x in this situation. Now we have an already factored form set here. We have negative 1/9 times x plus 18 times x minus 18. Now, their first step they show is multiply both sides by -9. Totally valid. But let's also make mention that in zero product property, if this times this equals 0, either this equals 0 or this equals 0 or this equals 0. Even the negative 1/9 counts as something. Either negative 1/9 equals 0, which is not possible, boom, or... So that's why they kind of can also ignore that. My goal is to find what values of x gives me 0, and negative 1/9 has nothing to do with that, literally. This could have been -9. This could have been positive 1 billion. It doesn't change what x values are going to make this thing 0. So that part didn't really matter as much. You're still going to have 0 on this side. Anyway, we end up solving this thing. You see the factored form. It looks like x will either equal -18 or positive 18. But they're asking for not just the answers for x, but the distance, the width of the arch at floor level. If this is -18 for x and positive 18 for x, the distance from -18 to 0 is 18. The distance from 0 to 18 is 18. And 18 plus 18 is 36. They probably did they did a subtraction. They mentioned absolute value, distance from 0. They get an answer with units, and it's all good. Okay, I'm going to go ahead and move forward into this stuff. I'm sure we're going to run into word problems with it along the way, so let's see what we have here. We're going to start with numbers 1 and 2, vocab and core concept check. Then we're going to hit our problem set 3 to 48, Description section down below will show the timestamp of each thing if you weren't paying attention at the beginning part. Okay, explain how to use the zero product property to find the solutions of the equation 3x times x minus 6 equals 0. Well, zero product property is once again a product that multiplies to become 0, and this is exactly one of those. We have a product of 3x times x minus 6 that is set equal to 0. Set each of those individually, I'm going to run out of room, equal to 0 and solve. So your goal of zero product property is to have a product set equal to 0. We have that. This is already in factored form. It's already there. So we're going to go ahead and set 3x equal to 0 and set x minus 6 equal to 0. And then we would solve. We would actually get x equals 0 and x equals 6 as our roots. It didn't ask find the solutions, instead explain how to. We're going to be doing a lot of practice with that. All right, so which is different? Find both answers. Okay, so let's mark one of them A and see what changes. Solve the equation 2k plus 4 times k minus 3 equals 0. Okay, so, we'll see what happens. Find the values of k for which 2k plus 4 equals 0 or k minus 3 equals 0. That's totally same as legit thing. If these two things multiply to equal 0, either this equals 0, boom, or this equals 0, boom. And that's the values of k we'd find. That's also an A. Find the value of k for which 2k plus 4 plus k minus 3 equals 0. That's a big no. That is a sum of values. It's way different. And there is no zero sum property, except the number has to be the exact opposite of the other one. But there's no either this equals 0 or this equals 0. That's why we are working on these things with products. That's why factoring is so important. So clearly this is the odd man out. Find the roots of the equation here. Boom. That's the same kind of thing as the others. Solve the equation, find the roots. You're finding the values of k that make it true. And that's totally it. So that's the one that's different. No sums. We're looking for products. Okay, I'm going to go ahead and move forward. We're going to look at the problem set numbers 3 to 48. We'll see how long this goes, and I hope that it works out swiftly. So let's follow along and take a look, starting with numbers 3 through 8, solving the equation. So we are going to attempt to solve x. Hold on, I need a lot less room there. All right, number 3. We have x times x plus 7 equals 0. This is factored. All of the problems that start with are factored. In factored form, this is what we want. We don't want to distribute. We want this product. Either x equals 0 or x plus 7 equals 0. Now x equals 0 is one of your solutions. Literally, if I substitute 0 in here, I'd get that answer. If I subtract 7 from both sides here, I would get x equals negative 7. So 2 solutions there. Very common thing to be witnessing, especially with only 2 factors. Or you could have one solution if it has repeated roots, which that one did not. Number 4. Let's try that again. Number 4. R times r minus 10 equals 0. Once again, either r equals 0 or r minus 10 equals 0. And I apologize if I sometimes don't put the word or. I'm just probably working through speed that way. So sorry if I don't. If r minus 10 equals 0, you add 10 to both sides and r would equal 10. So 3 and 4 looks going to be the same kind of question like that. All right, number 5. Number 5, we have 12t times t minus 5 equals 0. Now, I think it's worth mentioning, I don't think I brought it up in the lecture. Well, I sort of did with that negative 1/9. Remember, this also means 12 times t minus 5, meaning 12 is one of your parts of the product. 12t is not attached at the hip, as in I'm not required to put the 12 with the t in this in any sort of way. It's really saying either 12 equals 0, which is impossible, or t equals 0, or t minus 5 equals 0. But keep in mind, t equals 0 is my solution. Even if I put 12t equals 0, divide by 12, t still equals 0. There's no difference. So you can have it or not. I just want to make sure that you know that that 12 doesn't change the solution set. Add 5 to both sides, and t equals 5 as well. These are the roots. Number 6. Negative 2v times v plus 1 equals 0. Very much like number 5 in that same vein. This negative 2 has no bearing on the solutions for values that give me 0 as a final result. If negative 2v equals 0, and remember this is a product already factored, then v will still have to equal 0, right? The negative 2 is not the value that will become 0, but the v can by dividing both sides by negative 2. Subtract 1 from both sides, we get v equals negative 1. Here's an example where I never wrote the word or there as well. You can see where I can get kind of fast with it. Or is kind of necessary because, not necessary, but you don't want to use the word and because you can't be both at the same time, either one or the other. Number 7 has a product of 2 different quantities, s minus 9, remember that's not a 5, times s minus 1 equals 0. Either s minus 9 equals 0 or s minus 1 equals 0. I think pretty soon you're going to see me ditch writing out, say, that part, because you know adding 9 to both sides is going to get us 9 there. Like I could say s equals 1. Hopefully you know that 1 minus 1 is what gives you 0. So in the future, I think after this, as long as it's just one step away, you're probably going to see me putting that. I hope that's okay. After number 8. And on number 8, we do have y plus 2 times y minus 6 equals 0. So either y plus 2 equals 0 or y minus 6 equals 0. Subtract 2 from both sides, y is negative 2. Or add 6 to both sides, y equals 6. So there's the concept when it's already in factored form. You have to make sure it's set equals 0 before you start this thing. You have to make sure that it's an equation as well. I can't tell you the numerous different kinds of mistakes that students would make in these scenarios, solving expressions that aren't equations to begin with. Solving something when it's not actually set equal to 0. Oh, all that stuff super matters, and obviously that's probably going to apply to these questions coming forward. Okay, numbers 9 through 10 solve the equation. 9 through 20, solve the equation. These are also factored form, but they hit a few more bits with them. You can't just flip the signs on a bunch of these ones because there's more to be had in the problems. It's still 2 sets. A product of this times this equals 0. Either 2a minus 6 equals 0 or 3a plus 15 equals 0. If I add 6 to both sides and then divide both sides by 2, I will get a equals 3. So it's not just 6, it's not the opposite, because 2 times 3 minus 6 gives me 0. Subtract 15 from both sides here and then divide both sides by 3, you'll get a equals negative 5. So one or the other condition-wise works. You see a lot of more problems like that, but I think we're expected to see a lot of fractions showing up pretty soon. Number 10, we have 4q. Well, why don't you just use x? Come on now. I can't seem to write right there. There we go. 4q plus 3 times q plus 2 equals 0. Okay, either 4q plus 3 equals 0, or would you guys know what this would have to be? This one would have to be q equals negative 2. I'm not even going to go like farther on that one, but this one's clearly not negative 3. I will subtract 3, but then I also have to divide by 4. Q is going to be negative 3/4, and that fraction is perfect as an answer. But there are two answers, right? Two answers to this thing. And negative 3/4 and negative 2 are both of them. All right, number 11, we have 5m plus 4 quantity squared equals 0. Now, if you were with me on the notes, here's kind of what they brought forward, and you can choose to do it or not. There's more than one way to solve these, but I think, given what we've covered so far, I think I should work with the way that they're talking about it, which is squaring something means multiplying something by itself. 5m plus 4 times 5m plus 4. Now, you'll notice here that this represents the same thing, to say either 5m plus 4 equals 0 or 5m plus 4 equals 0. For the sake of this first problem, I'm going to go ahead and write it that way, that it's the same thing twice, either one or the other. If you subtract 4 from both sides and divide both sides by 5, you get negative 4/5. It looks like that's going to be the same thing here. M would have to be negative 4/5 there. Well, that's the same thing twice. Do you have to write both? I'm going to say no. The concept is that's the only value that works with it, but it's known as a repeated root. There is actually importance to that in the future, which I mentioned in the notes, but you don't have to really necessarily write it twice. And I don't think I'm going to write it twice for this next one. Number 12, if h minus 8 quantity squared equals 0, then either h minus 8 equals 0 or h minus 8 equals 0. Right? Therefore, straight up, h equals 8. I mean, first of all, it's the same thing twice. Second of all, it is one of those basic ones. I'm dividing both sides by 1 in the end. It's just the opposite. 8 minus 8 is what's going to give me 0. I think it makes sense to be able to write that answer, especially after recognizing what we did before that. Okay, number 13, we have 3 minus 2g, 3 minus 2g times 7 minus g equals 0. So now we have variables on the right side of this thing. That doesn't really change anything. Our goal is to still solve for g. 3 minus 2g equals 0. Maybe this gives you more trouble for 7 minus what would be 0. Obviously, that value appears to be 7. So decide how you want to work on this. If I subtracted 3 from both sides, then I'd have to divide both sides by negative 2, and g would be positive 3/2. That's how that works, and negative divided by negative is a positive. Or I could add the g to both sides. In this case, 7 would equal g, or g would equal 7, right? Just rewrite that in that order, but that's by adding g to both sides. I mean, you can kind of work whichever way you'd like. Your goal is to solve, and it seems like they're kind of tricking you with it, so you don't get too confused. But this is also why standard form is always so important for me, that I write that thing in the way that's going to have the variable terms first when it comes to factoring, because this can get a little oddballish. I mean, I know what I'm doing with it, but I just don't like the look. This is also set equal to 0. Seems like all of these are for this set. So either 2 minus 4d equals 0 or 2 plus 4d equals 0. Subtract 2 from both sides and divide both sides by negative 4. You get 2/4 or 1/2 as a reduced fraction. Here I subtract 2 from both sides and I divide both sides by 4 and I get negative 1/2. Kind of one of those difference of two squares bits when you multiply that thing out, which is not what we're doing, but I'm just saying that those are the two solutions, positive or negative 1/2. All right, number 15 and onward looks like it has more than two factors. So on number 15, we have z times z plus 2 times z minus 1 equals 0. Now, once again, this is a three-set thing. Either z equals 0, this guy on the outside, or z plus 2 equals 0. So z would equal negative 2, or z minus 1 would equal 0, so z equals 1. And I'm going faster with those because it is just the opposite. As long as it's a 1z, it works out. Those are the three different answers, three factors, no repeated roots, three answers on that. And again, three answers, I think, on pretty much the rest of these, unless there's a repeated root. I have 5p times 2p minus 3 times p plus 7 equals 0. If 5p equals 0, once again, it's one of those things. If 5p equals 0, divide both sides by 5p equals 0. Once again, the 5 has no bearing on this, guys. This could have been a 55. P still equals 0 right there, right? That's the thing. So p equals 0, 5p equals 0. This one I might want to spend more work on. 2p minus 3 equals 0. We add 3 to both sides. We divide both sides by 2 and we get 3 halves. Maybe you can do that mentally. I mean, I can. Maybe you can. It's just better work to probably write those ones out to recognize when they happen. And then P, let me write that better. P equals -7 is that third one. Again, I don't think anything really needs to be written out for that. But 3 solutions, all good to go. Number 17, we have r minus 4 quantity squared times r plus 8 equals 0. Once again, the squaring is not really doing anything to affect me with this. If you set it up in zero product property, it's either r minus 4 equals 0, r minus 4 equals 0, or r plus 8 equals 0. It's still r minus 4 equals 0. You plug in 4 into here, you're going to get 0 out. 0 squared is 0 times anything is 0. So r equals 4 is one of them. R equals -8 is one of them. And I don't want to dismiss showing work. That's not my intent here. It is once you recognize a pattern with it, you use it when you can. I'm not trying to not show work. I'm trying to only show work when necessary because of the concept of the problem. Same thing with this one. If w times w minus 6 equals 0, either w equals 0 based on that, or w minus 6 squared, or w equals 6. Right? It's once again the opposite of that. And hopefully we get a squared one that has things that we have to work off of, like, dividing by something as well. We'll see. Number 19, we have 3 factors, but the variables are kind of all in disarray. So maybe it's worth writing this thing out. Actually, I think it really is. Setting them equal to 0 separately and solving for them. So 15 minus 5c times 5c plus 5 times -c plus 6 equals 0. So either 15 minus 5c equals 0, or 5c plus 5 equals 0, or -c plus 6 equals 0. Let me just take care of that last one first and talking about the answer is not -6, or not necessarily -6, because that c is opposite. It's a -1, so we'll have to do something with that in a bit. Let's start from the beginning here. I'm going to add 5c over just to turn it positive. Then I divide both sides by 5. It looks like we get a c value of 3. You could double check that. 15 minus 5 times 3 should give you 0. Maybe you know this answer as well if you kind of think about what you can substitute in. But if I subtract 5, then divide both sides by 5, I'll get -1. And lastly, I could subtract both sides by 6, but I still have to divide both sides by -1, right? Switch the signs, that would give me c equals 6. And that makes sense. -6 plus 6 gives me 0. 3 different answers, one or the other, or the other. That is number 19. Number 20, they give us a fraction in one of the sets here. Let's make sure we know how to solve with a fraction. So on number 20, we have 2 minus n times 6 plus 2/3 n times n minus 2 equals 0. I think I'm good on this this last one, I should say. N equals 2 is one of them. Maybe you can notice here that n equals 2 is once again showing up, right? 2 minus 2 would give me 0. Pretty straightforward. This one maybe not as straightforward. Even I myself thought about it. I think it's -9. Got it for a second, but let's set that one equal to 0, and let's talk about how to solve with that fraction. Or this equals 0. I'm going to subtract the 6. 2/3 n equals -6. And to solve this in one step, I would multiply both sides by the reciprocal, 3 halves, times 3 halves like that. 3 over 3 and 2 over 2 becomes 1. We're left with 1 n equals. -6 times 3 is -18. Divided by 2 is -9. So n equals -9 is the third one, and that's the result. Now remember, 2 minus -9 isn't 0, right? But the point is it can plug into this one, and when you multiply 0 with anything, you get 0 out. And remember, n equals 2 was a repeated root. I really don't need to write it twice, but I did. In exercises 21 to 24, let's find the x-coordinates of the points where the graph crosses the x-axis. Now they give you a drawing, and I think they're really setting up the concept of what this will be dealing with when we do graphing eventually. I think it's in chapter 3, but as a big whole. But here it says find the x-coordinates of the points. They give you an equation, they give you a roundabout where it's supposed to be, but the idea of x-coordinates, x-intercepts are values of x when y equals 0. So let's substitute 0 for y here. X minus 8 times x plus 8 equals 0, and let's find those values of x. So the x-coordinates here, x would equal 8 is one of them, and x equals -8 is the other one. They say find the x-coordinates. They don't ask you to write the ordered pair out, so that's there. And that seems to make sense when you look at this thing. That looks like -8 here and +8 there. I think I'm in agreement with that. And I do believe that should be the answer. Number 22, same thing. Let's set y equal to 0 on these, and maybe you can imagine what happens as we change some signs around. Y equals x plus 1 times x plus 7. We're going to set y equal to 0. X plus 1 times x plus 7 equals 0. So either x would equal -1, once again, it's one of those fast ones, or x equals -7. Those are the x coordinates, and you can look at that graph to compare and say, does it make sense that that's -7 and -1? Yeah. And these are those graphs, by the way. If you go to a graphing calculator, we have some parabolas. That's something going on in the future for sure. We're going to be graphing parabolas down the line, and we'll see what they look like then. Oh, we have 2 more graphs on these. Number 23. Number 23, a negative graph. What makes a parabola flip upside down? Making something negative, just like absolute values. Y equals negative x minus 14 times x minus 5. Does that negative actually affect? It affects the graph. Does it affect the x-intercepts? I'm sure that this, as a book, if this was one of the examples, or if we had an answer key, it would say, first let's divide both sides by -1, which I totally get. The concept of this is the -1 has nothing to do with what x values is going to give me 0. So if I divided both sides by -1, I get the same thing there. Either x minus 14 equals 0, where x equals 14, or x minus 5 equals 0, where x equals 5. And the negative had no bearing on that. Because -0 is still 0. And that's not going to change it. And then number 24, that same thing. That -0.2 is really just in there to bother you. It's doing nothing. If it said -0.2x, if it said -0.2x, it still would be doing nothing because it's still multiplying by x. Remember, x is no different than x plus 22 when it comes to being part of a product. It's just multiplying by it. And I need to stress that importance because people assume only things in parentheses multiplying. No, they would anyway. Anyway, the -0.2 is going to have no effect on it when we, it has an effect on your graph. It doesn't have an effect on what values we plug in for x to get 0 out as a result. And each of these times, guys, I'm setting y equal to 0 because those are the, y equals 0 is where we cross the x-axis. So x equals -22 seems to be like one of those. You see this massive scale, and somewhere between 10 and 20 looks like, or 10 and 20 looks like the next one. Looks like that is 15. X equals 15 there. Okay, that's the 21 to 24 on, not graphing, but finding the x-intercepts for it. Let's look at 25 to 30 and factor the polynomial. There's no solving to be had. The only practice is factorization. So this is our first one together that we get to look at, minus the examples, but we get to actually work on together and fill in the blanks with them. So 5z squared plus 45z. Let's factor. Now this factoring sense, and by the way, I'll be mentioning this in future videos, so you're good. But our factoring in this case is greatest common factor. You always look for greatest common factors when it comes to factoring. It should be the first thing you look for, period, even if you do more complex versions of what factoring will become. You're going to hear me say that again in other videos. Greatest common factors first, always. I don't know if the book will say it. I hope it does. But it will absolutely follow it. You're going to hear it say factor completely. I guarantee you it's going to say factor completely, which means greatest common factors are a part of it. All right, greatest common factors. Let's find a number that can divide out of 5 and 45. And by the way, if it can't, then you don't divide a number out. But you can. You can divide out 5. Right? You divide out 5. And how about out of z squared and z? What's the most amount of z's that can pull out of both of them? Not z squared, because z only has one z on it. But here I can pull out at least a z from it. And that's the ultimate goal when it comes to solving these eventually. Getting this thing out of here turns it into a linear equation, which is nice. What remains inside? Factoring is the opposite of distribution. If I distributed a 5z, multiplied it by something here to get 5z squared, what would it be? Well, the 5 is still the same, so that would be a 1. But z times z is z squared. So 5z times z is 5z squared. You factor the 5z out, z remains. And then plus 5z times what is 45z? The z is still the same here, but 5 times what is 45? 9. And that's the factorization of it. And you can always double check by doing two things. One, exactly what I was doing, kind of distributing back in to see what comes as a result. And two, your other double check is to see if anything else can factor. Is there any other common factor that exists among z and 9? No. No numbers, no variables. If you factor the things properly, there shouldn't be any variables left over inside of it if you are factoring as many versions of that one variable as possible. So far, we only see one variable per problem, so I'm going to go and stick with that. All right, 6d squared minus 21d. You cannot divide 21 by 6, but you can sure divide it by 3, just like the 6. I'm going to factor a 3 out, and I'm also going to factor a d out of both of these here as well. 3d times 1 is 6d squared, 3 times 2 is 6, and d times d is d squared. 3d times 2d is 6d squared. Minus, I should follow that along. 3 times what is 21? Well, 7. And it looks like a d remains, so that's what we're going to have there. Once again, if I distribute it back, I get this, and note there's no common factor that is shared here. No more d's, and 2 and 7 cannot factor out any further. Okay, number 27, 3y cubed minus 9y squared. This is our first instance, I think, of seeing something that's more than just being squared to begin with. But we can still, if we have a common factor, we'll still go for it. There's something else I want to mention about factoring. It hasn't shown up yet, and I don't know if it will. Depending on the certain kind of problem, I'll just go ahead and say it to begin with. First of all, you want to be in standard form. I'm just going to stress you want to be in standard form. But secondly, if your leading term is negative in standard form, you factor out the negative. You'll have noticed, if I went back to previous problems, like this negative here, this negative is factored out, this negative is factored out. You're not going to leave an x with a negative inside of there and one of those things. You won't want it. Just trust me on this right now. Now, this is in standard form. The leading term is positive, so I'm all good there. I just wanted to mention it. Okay, factor a 3 out of 3 and 9. Remember, factor to us means division. We just got to write the result, though. And I can factor as much as y squared out of this, because I'll still have a y left with this y cubed. 3y squared times y is 3y cubed. And then right here, I factored out all that y squared, but 3 times 3 times 3 is 9. And 3y squared times negative 3 is negative 9y squared. That's the factorization. Once again, I'm not solving anything. These are expressions. They're not equations. I don't start saying, well, therefore, y equals 0 and 3. That's not how that works. My stylus is kind of getting funky right now. No, that's not how that works. This is not an equation. There's no zero product property if we're not set equal to 0, especially in no equation. Number 28, 20x cubed plus 30x squared. 20x cubed plus 30x squared. 20 and 30 can both divide at most by 10. Sure, it can divide by 2 and 5, but also 10. And x squared is the largest one. Once again, if you're in standard, here's the benefit of standard form. If you're in standard form, you know that the most x's that can divide out are the ones from the last term in the list. If there are x's that can divide out. I'm waiting to find one that can't. Doesn't seem like that we're running into those. Which makes sense probably for this problem set, because our whole goal of factoring is to create a scenario where when set equal to 0, I can now solve these separately. 2x plus 3 and 10x squared equal to 0, I could solve separately. Fine. Together, I can't. All right, 29. 5n to the 6th power plus 2n to the 5th power. This is the first example of a problem where no number could factor out. I can't, 5 and 2 are prime numbers. I can't divide any number other than 1 out of 5 and 2, so I'm not going to take any numbers out. That doesn't mean it's not factorable at all. I can pull out a whole n to the 5th from this thing, a 1n to the 5th. So n to the 5th times 5n is 5n to the 6th. That number's going to stay there, and this 2 is going to stay there as well. N to the 5th times 2 is indeed 2n to the 5th, and it looks like that. Totally valid for our problem set. That's the answer. Just no numbers factored out, only variables, which is the more important part. Once, I think I've said that more than once, is the more important part when it comes to solving them when they are equations, the variables. That's what creates the product property and getting what you solve for. And lastly, 12a to the 4th plus 8a. 12 and 8 both have a greatest common factor of 4, and that a can also factor out of both terms. A times a cubed would be a to the 4th, and 4 times 3 would be 12. 4a times what is 8a? A 2, a positive 2, and there is the factorization of number 30. All right, this is going pretty swimmingly. I'm sure the very last problems in the set are the word problems, so we're saving those for last, but we're getting near there. Oh, I think we go to 48. I was thinking we're going to 43. Darn, we're not even 2/3 of the way done then. All right, now number 31, solve the equation. This is the beginning of solving quadratics, and I think these all look like quadratics, in such a way that you want everything on one side of the equation, preferably standard form. That's going to be for me. Preferably standard form on one side of the equation. Find the greatest common factor because there are going to be multiple terms with variables in them. And then solve using the zero product property. So, step 1, factor. Create a product out of... step 1, set equal to 0. It is. Step 2, factor. Create a product out of this thing with the greatest common factor, especially with the variables, more so than anything else. You can deal with numbers not being factored out and still solve. Step 3, solve using the zero product property. Okay, a p can factor out of both terms, and that's it. No numbers. P factors out, a 1p. So I still have 4p inside of here. P times 4p is 4p squared. And p times what is negative p? Negative 1, right? So I've created a product out of this, set equal to 0. This is now a stage where we solved. I've done a bunch of these problems so far, probably like 20 of them. This times this equals 0, either p equals 0, which is one of the answers, or 4p minus 1 equals 0. Whoops. 4p minus 1 equals 0, in which case I will add 1 to both sides, and then divide both sides by 4, and I get p equals 1/4. Now, I'm not going to be big on double checking this whole part here because you'll have trouble with it, but 0 is going to be pretty easy. I can substitute this in the original equation. 4 times 0 squared is 0. Minus 0, 0 minus 0 equals 0. If I substituted in 1/4, I would indeed get 0 back out, but there's this whole concept of kind of working that out, and I don't want to deal with that. But that is what would do it, and factoring helped us solve that. That is the ultimate goal. Okay, number 32, 6m squared plus 12m equals 0. Let's go through our checklist once more. Is it set equal to 0 in this equation? Yes. Is it a factorization? No. So let's factor the GCF from this thing. 6 and 12 can both divide 6 out. M squared and M can both divide out in M. Oh, I should also ask, set equal to 0. Is it in standard form? Maybe not a requirement, but I think it'll feel a lot better that way. So you'll see me use standard form, which is only 2 terms for each of these, so not too hard to do. Anyway, 6m times m is 6m squared. 6m times 2 is 12m. I'm factored. So either 6m equals 0. Divide by 6, you get m equals 0. Once again, one of those things, I don't really think the 6 had any bearing on it. I know it didn't. Or m plus 2 equals 0, so m equals negative 2. And once again, I'm going to probably be skipping that step in between for a problem like that in the future. Number 33, 25c plus 10c squared equals 0. See, this is an example where it's not in standard form. And that's not to say that it's any worse. I just don't like it as much. I'm going to rewrite it in standard form. It's not going to change your answers unless you end up getting it wrong because of the way that it was written. So rewrite in standard form, already set equal to 0. I'm going to find greatest common factor of 5 from these things and a c. Again, the last term, when written in standard form, factor of 5c out. 5c times 2c. 5c is 2c, 10c squared is what it multiplies to. And 5c times 5 is 25c, and there's my factorization. If 5 times c equals 0, then c equals 0. The 5, once again, has no weight on that. If 2c plus 5 equals 0, see, the book skips this 2 steps in between. I subtract 5 from both sides to make it negative, then I divide both sides by 2. c is negative 5 halves. Again, they were subtracting from both sides to begin with, and then dividing both sides by 2. Number 34, once again, also not in standard form. This is, I am going to make a bit of a stink about this. Not stink as far as what the book says, but what I was bringing up before. This is where, I'll do it more than one way. Maybe you're like, hey, Mr. Robinson, it's set equal to 0. I just want a greatest common factor. Fine. We'll find a greatest common factor from these. 18 and 2 can both divide by 2, and q is the smaller of those things here. 2q times, and here we have 9. Boom. Minus, it looks like 1q. 2q times 1q is 2q squared. So 9 minus q equals 0. If 2q equals 0, then q equals 0. If 9 minus q equals 0, well, 9 minus 9 would equal 0, right? Q equals 9. So it wasn't terrible to do, but there is something greater when it comes to standard form being a requirement in some later kinds of problems and what we do, and it really is suggested that you do it in other situations when called upon. Now, if I keep them on this side of the equation, here's what happens in standard form. the first term becomes negative. Now, I wanted to have one of these problems just to mention. If your leading term is negative, and I don't mean in this case leading term, I mean in standard form, if your leading term is negative, factor the negative out among everything else. Now, instead of factoring a 2q out, because that's still a greatest common factor, I'm going to factor the negative 2q out. Factoring out negatives is an important practice with this. It is. But factoring a negative out, negative 2q times q is negative 2q squared, and negative 2q times negative 9 would give you positive 18q. Negative times negative is a positive. You would still get the same answers of q equals 0 and q equals positive 9 in that case. But, you might be asking why for the negative thing. Just right now, just trust me on it. Maybe I can talk about them with future examples and why it's going to matter more. But there's a cleanliness to it. There's something that's going to apply a lot better for you. All right, number 35. Now it's not set equal to 0. We go back to the whole thing. Is it in standard form set equal to 0? No. This time, we have to first set it equal to 0. I'm going to subtract over 9n so I can keep the n squared term positive, and it's in standard form. And now I can go ahead and play the factoring game. Factoring isn't just division. It's taking an expression and pulling things out that when you multiply it back in, it becomes there. But they have to be on the same side of the equation first. So 3n can factor out. 3n times n is 3n squared. 3n times negative 3 is negative 9n. If 3n equals 0, then n equals 0. If n minus 3 equals 0, then n equals 3. You can see where my speed starts coming along here because we're practicing other parts like the factoring portion, setting equal to 0, and we've seen a lot of those now. Number 36, we have negative 28r equals 4r squared. Now, I could subtract 4r squared over and set it equal to 0, but like I said, I want to keep this one positive if possible, so I'm going to add 28r to both sides. I don't like writing my 0 on this side, though, so I think I'd rather write everything on the other side as 4r squared plus 28r equals 0. It's just a little OCD thing, but I think you would agree once you do this as often as I have. You can factor a 4r out of here, 4 from both of these numbers, and r is the variable. 4r times r is 4r squared, and 4r times 7 is 28r. If 4r equals 0, then r equals 0, and if r plus 7 equals 0, then r equals negative 7. Now, once again, there are other instances of things that you could do. I could have divided both sides by 4 to begin with, but you cannot divide the r's. You cannot, because 0 is one of your answers. That would be saying dividing by 0. You'd be getting rid of that solution. It's just not something that you can do. All right, error analysis. Let's see where they mess things up here. Describe and correct the error in solving the equation. 6x times the quantity x plus 5 equals 0. So x plus 5 equals 0, and you subtract 5 over, you get x equals negative 5. We get the root is x equals negative 5. Well, they forgot about the 6x portion. The 6x factor was not, and really it's not 6x, it's x, but the 6x factor was not considered for a possible solution when it is a part of the product of the 0 product. Right? Two things multiply to become 0. So we also have to solve that one. So describe and correct the error. That's the description. Let's go ahead and correct the guy. 6x times x plus 5 equals 0. Either 6x equals 0 or x plus 5 equals 0. We saw that x equals negative 5, but when you divide both sides by 6, you also get x equals 0. There's more than one solution, and the x equals 0 is the other one. So it can't be ignored. Maybe because it's outside of parentheses, people forget about it. I'll tell you what people tend to put a lot. I talk about mistakes people make. You say, right here, you get used to this whole switching the signs, man. X equals negative 5. You know what people put here? X equals negative 6. No, I don't think 6 times negative 6 gives you 0, right? The whole goal is what gives you 0. So that's why setting up, don't rush steps that you wouldn't otherwise know how to do. So just be careful when we're hitting those. All right, one more error analysis. Let's do it. Let's do 38. 3y, hold on. We got to describe the error first. 3y squared equals 21y. 3y equals 21. Y equals 7. The root is y equals 7. This goes right back. I'm glad they have this. This goes right back to what I mentioned. You could divide both sides by 3 at some point. That doesn't affect your solutions. You'll be doing it at some point anyway when you factor. But this is why we factor out variables, not divide them. They divided both sides by y. they effectively canceled, or in America we use 1L, they effectively canceled out one of their solutions. And this is something when you see the answer, and they also divided by 0. See, the other solution is 0. What, 3y squared equals 21y? That the value 0 works there. You can't be dividing by 0. You say divide both sides by something. Well, if y equals 0, then you do that. So you can't do that. So what are you going to do instead in this situation? You're not going to divide both sides by y, but you're going to factor out a y. And that can only happen if you move the 21y to the other side of the equation, set this equal to 0, and use that 0 product property. We'll factor out a 3 from 3 and 21. We'll factor out a y from y squared and y. And now you're left with 1y minus 7. And yeah, y equals 7 is one of your answers. But you know what? You forgot one. Y equals 0. So it seems that there are different ways where you might be ignoring that 0 is one of the answers. Again, I promise you that that's something people do. If also I mentioned the whole, you might say y equals negative 3. In these cases here, people would also say, y equals 1. No, y doesn't equal 1 either. Y equals 0 in that instance. So again, just be very aware of what's going on. Make sure you know the math that you're doing. Don't just try and follow steps unnecessarily. All right, modeling with mathematics. We had one of these in our example set. So if you checked that out, this is going to look very familiar. In fact, they say see example 5 because it looks like it. All these are parabolas. They're all quadratics. The entrance of a tunnel can be modeled. I don't know if I want to drive in that. I might hit the sides. The entrance of a tunnel can be modeled by this equation here, where x and y are measured in feet. The x-axis represents the ground. Find the width of the tunnel at ground level. Okay, so we have negative 11 over 50 times x minus 4 times x minus 24. You might be wondering why they have such a weird number here. For the sake of the graph, they wanted to go upside down. They wanted a specific vertical compression to say that this tunnel is probably about 22 feet tall, just to kind of make it accurate to tunnels. That's fair and that's fine. So, but the question is, does the negative 11 over 50 have anything to do with our solutions for x when we plug them into, by the way, I'm going to set y equal to 0. To get 0 out, the answer is absolutely not. It has no bearing on the answer. When it comes to 0 product property, we're once again saying if this times this times this equals 0, either this equals 0, which is impossible, I can just ignore it, or multiply both sides by negative 50 over 11, or x minus 4 equals 0, so x equals 4, or x minus 24 equals 0, so x equals 24. Now, I feel like I skipped some steps in the description of what this problem is asking and what we're representing. They mentioned that the x-axis represents the ground level. So when we're driving on the ground, this bottom right here is that ground level. And they want us to find the distance between the 2 points, or excuse me, between the endpoints of the tunnel right here. Find the width of the tunnel at ground level. So they want to find out what x value this is and what x value this is. And the x-axis is what the values of x when y equals 0, their x-intercepts. That's why we substituted 0 for y. Now, did I solve this problem? Not quite. I found the positions of 4 and 24, but 24 minus 4 would give us 20. And this is measured in feet. So this is in feet as well. Now, I guarantee you that the book's solution guide somewhere would use absolute values, which is nice because 4 minus 24, I'd also want to just mention as like 20. It's the distance between those two. So 20 feet ends up being the answer. Now, if you look at the graph thing, I think it makes sense that that's 4 and 24. Here's 8, and here's half of 8. And then here's 12, 16, 20, 24. So even looking at those would work out. But of course, 0 product property is probably the bigger practice. Okay, the Gateway Arch in St. Louis can be modeled by this. And by the way, I believe that it actually is a parabola. There's some whatever scientific things that having it as a parabola is very helpful. So it's a quadratic equation. So it can be modeled like this, where x and y are measured in feet. X represents the ground. Okay, so find the width of the arch at ground level. So once again, we have this equation here. X plus 315 times x minus 315. Now, as much as the answer probably is x equals well, it's not the width, but as much as the 0 product property thing would say x is negative and positive 315, you don't do that unless it's set equal to 0. This is set equal to y. Because the x-axis is ground level, though, we will be setting that equal 0. But don't skip any steps along the way. Set it equal to 0 before you solve. Otherwise, you're not solving for the right thing. You're going to end up doing it when it's not set equal to 0, when it's set equal to 2, and then it'll be wrong. Again, this part is no bearing. X either equals negative 315 or x equals positive 315. And I think this is the actual width. I think that they are actually correct when they say this. So we're going to be doing, the absolute value of negative 315 minus 315. We're taking one of the answers minus the other answer. An absolute value because we just want a positive answer out. That becomes absolute value of negative 630, which is 630 feet. Likewise, we could have also done 315 minus negative 315, which is 315 plus 315, which is still that. But you'd still want it wrapped around absolute values just to make mention of what the heck is happening for the thing here. You get 630 feet no matter how you go about that. All right, that's part A. Find the width. Part B, how tall is the arch? Now, the tallest point, this is actually kind of interesting, and this is where this number actually will have some bearing. The tallest point, if you notice, is on the y-axis. And it doesn't look like it's hitting something on this it's 700, but it's on the y-axis. Now, we've been practicing that ground level x-axis is when y equals 0. Well, now we're finding a y value on the y-intercept, and that's when x equals 0. So what I'm going to do this time is substitute 0 for x. I don't remember this question popping up in the example set. Maybe I skipped it. But 0 plus 315. Oh, good. This is a 315 on this part. 0 plus 315 is 315. 0 minus 315 is negative 315. All right, here's what we're going to do. 315 may be multiplying with that and by 2, but it's also dividing by this 315. 315 over 315 is 1. And now you're left with negative 2 times negative 315. You know what that is? That's also 630. 630 feet. So yes, I actually don't know if I remember that part. But yes, the gateway arch is just as wide as it is tall. So I don't know if that parabola in nature allows it to do something that's special, or if that's even actually accurate. I think I've seen that in examples before, or in books, like I said. So hey, there's something to it. We can look up why it's a parabola later, but furthermore, why it's as tall as it's wide. I don't know. All right, 8 more problems. Number 41. A penguin leaps out of the water while swimming. This action is called porpoising. The height, y, in feet of a porpoising penguin can be modeled by y equals negative 16x squared plus 4.8x, where x is the time in seconds since the penguin leaped out of the water. Find the roots of the equation when y equals 0. Explain what the roots mean in this situation. So I'm going to first set y equal to 0 in this situation, plus 4.8x equals 0. And now I'm going to solve this thing. Notice that, and I think I mentioned this before, the negative 16 portion has to do with gravity. Penguin jumps up, gravity's pulling it down. It's an acceleration thing. 4.8 is probably the speed at which it came out of the water. In what, feet? In feet per second. Okay, so this guy is negative. The leading term is negative. So there are ways you can do factorization of this, but because this is already not an integer, I don't think I'm going to play with it in that way. But at the very least, I'm definitely going to factor out variables, and I'd love to factor out this negative. It's a personal thing for me. So although there's no GCF of 16 and 4.8 in the way that we'd like to not have any decimals in the result, I can still factor out a negative x out of both terms. The negative 1 from both terms will change our signs, and the x is the big thing that will allow me to solve for this thing. Negative x times positive 16x gives me negative 16x squared, and negative x times negative 4.8 would have given me positive 4.8. So one of the solutions here, if negative x equals 0, and again, the negative really has nothing to do with this, then x equals 0. That's one of the answers. Or 16x minus 4.8 equals 0. Now, I actually don't know this answer. I'm going to go ahead and add 4.8 to both sides and then divide both sides by 16. And I get 4.8 over 16. Now, 48 over 16 is 3. So 4.8 over 16 must be 0.3. That's, I guess it's right, but that seems really fast. I guess penguins don't really porpoise for very long. If that's, it's less than 1. I mean, it's less than 1, but it's just, that's super fast. So it says explain what the roots mean in this situation. These are both of the roots of this thing. So this basically means that x is the time in seconds since it, let's see, where x is the time in seconds since it leaped out of the water. So the penguin porpoised out of the water. Hey, porpoised is a word. At time 0 seconds, and hit the water again and went back into the water. Let's see, what did it say? Leapt, yeah. Went back into the water after 0.3 seconds. That's what I was saying. It doesn't seem that long, but actually that now seems a little more normal. I mean, half a second, it's less than half a second, but it's probably... Okay, that's fine. I mean, gravity takes hold. It's not going super high and out of there. All right, that's 41. 42, how do you see it? Use the graph to fill in each blank with the equation in the equation with the symbol plus or minus. Explain your reasoning. So number 42, we have that graph. I'm going to go ahead and kind of point more at this one and talk about what's there, and then I'll just write the answer on the other side. Okay, so this parabola has 2 x-intercepts. These are kind of important. The book's really talking about x-intercepts long before we hit them with graphs, which is pretty nice. I imagine that's why they have to bring it up. But x-intercepts right here are values of x when y equals 0. So if you imagine for this y equals equation that we're talking about, let's start with equals 0. Let's talk about, got an x and a 5. That's apparently our scale, and they don't want to reveal it to us because otherwise it would give away the answer. If these equaled 0, you have to think about what those x-intercepts would be to make that happen. The x-intercepts would have to be this guy, a negative number, and this guy, a positive number. Now, based on, even though we don't see the numbers, it looks like this would have to have been a negative 3, and this would have to have been the positive 5 just by distance. So if x equals negative 3 is one of our roots, and x equals 5, I'm sure I could have explained this better, and x equals 5 is one of the roots, then that means that, when set equal to 0, what value of x do I plug in to get 0? Negative 3. That means this would have to be a plus 3. It's one of those kind of change the sign things, and this would have to be x minus 5 as a result of what we have there to make that happen. So the equation should say y equals x minus 5 times x plus 3. You're really asking yourself if I had, what kind of equation would I have to make that graph? And that would be the positive 5 because it looks farther out when it comes to the parabola. And that would be the answer. Okay, number 43. How long have we gone? Just a little over an hour. Number 43, critical thinking. How many x-intercepts does the graph of y equals 2x plus 5 times x minus 9 squared have? Explain. They really are getting a little bit into not only the intercepts, but also this multiplicity thing. So 2x plus 5 times x minus 9 squared. X-intercepts are, again, when y equals 0. So let's set y equal to 0. Let's get 2x plus 5 times x minus 9 squared equals 0. It's already factored. So using the zero product property, either 2x plus 5 equals 0, and then you subtract 5 from both sides, and you divide both sides by 2. You get negative 5 halves. This is one of the x-intercepts. This is somewhere it crosses the x-axis. But also x minus 9 squared equals 0. Now what the book would likely do is give you that x minus 9 times x minus 9 talk, and either x minus 9 equals 0 or x minus 9 equals 0. So x equals 9 or x equals 9. And then you sit there and go, if I have 3 solutions, that must mean I have 3 x-intercepts. But hold on, this x equals 9 appears twice in there. So it's not that x doesn't equal 9, but it's that it's a repeated root. And a repeated root is also a repeated x-intercept. Now, as a graph, there's something really special that actually happens at x equals 9. It doesn't just cross through like anything else. That's something you'll do in IM3. But there are only 2 of them. There are 2 x-intercepts. They say explain. It's because one root is repeated. Now, they don't ask us to look at what the graph looks like. Once again, more of an IM3 thing. When you get into that, you'll understand. But there are 2 x-intercepts. Whoops. 2 x-intercepts here. Okay. And that's number 43. I thought critical thinking was generally an open-ended, no, thought-provoking, there it is. Thought-provoking is an open-ended kind of question. All right, number 44, making an argument. Your friend says, I don't really have math friends. Your friend says the graph of the equation y equals x minus a times x minus b always has two x-intercepts for any values of a and b. Is your friend correct? Explain. Well, I don't have anything to write except for typing here. But x minus a times x minus b, it always has two x-intercepts for any values a and b. They don't seem to state that a and b can't be the same number. So that means they can be the same number. And if they are the same number, then you'd only be looking at one x-intercept. So no, your friend is not correct. I don't know what kind of friend is even coming up with. Friend or not, I don't know, math geek or not, who's coming up with this kind of argument? No, your friend is incorrect. If a and b are the same value, then you have the same x-intercept from a repeated root. Therefore, it won't always have two. Okay, so that's a pretty good explanation. Any other situation, yeah, there'd be two x-intercepts and you'd be good. Remember, x-intercepts, value of x and y equals 0. That whole factored form lets us use zero product property to refer to what those x-intercepts would be. They would actually help us solve it. All right, 4 more. Number 45, critical thinking. Does the equation x squared plus 3 times x squared times x to the fourth plus 1 equals 0 have any real roots? Explain. Well, we're in factored form here, and in factored form we can say x squared plus 3 equals 0, or, and here, x to the fourth plus 1 equals 0. Now, I have to be careful how I talk about this problem because I don't know to what instance you've done certain solving mechanisms. You haven't solved using square roots or fourth roots before, but let's just talk about the concept that we have right here. Well, I'm going to subtract 3 from both sides. Let's just talk about the concept that we have right here, given that you probably haven't taken roots of things to solve for. So if we have this setup here, you know, there's a way that you solve by taking square root, the fourth root, and stuff like that. But do you get real roots out? Real roots meaning values that, well, there are complex imaginary numbers, and that's what these ones get. What you got to think about is when you square a number, what happens to it? When you raise a number to a fourth power, what happens to it? No matter what it was originally, if it was a real number that you squared to raise the fourth power, it'll turn positive. These results are negative. How do you square a number and make it negative? For real numbers, you can't. For imaginary numbers, you can. And I'm sorry, imaginary numbers aren't any less real than real numbers. That's just the name of them. But what is this? Does it have any in real roots? Explain. No, because you cannot raise a real number, a real number, to an even root and get a negative and obtain a negative result. And that's exactly what we're showing right there. That real numbers raised to even roots. Odd power, totally fine. That's probably why they didn't ask you to do it, because you probably don't know how to solve it just yet. But that's the reason why it doesn't work. All right, number 46, thought-provoking, which also means open-ended. So, thought-provoking, write a polynomial equation of degree 4, whose only real roots are x equals 1, x equals 2, and x equals 3. Okay, this does kind of go back to that graphing one when it comes to, if these are the roots, then that means that x minus 1 equals 0, x minus 2 equals 0, and x minus 3 equals 0. That means that in a factored form version, I could multiply x minus 1 into something to get 0, or x minus 2, and or x minus 3, and I would get that. So this would be a polynomial equation that would work out. Eventually, they want us to change this into y as well to make it something that you could graph and such. But they're talking about, well, actually, I don't think so. They just said the roots, right? I think we need it equal to 0 still. But this is not degree 4. This is degree 3. This is something raised to the first power times something raised to the first power times something raised to the first power. And if I distributed these things all out, I'd be left with an x cubed. X cubed is degree 3. To get degree 4, we got to square one of these. So, as far as open-ended goes, this could be an answer, or this could be an answer, or this could be an answer. And anything else that's multiplied outside. I could have a 5 out here. I could have a negative 5 out of here. Doesn't change the result of that. And if I square one of them, let's square that middle guy like that. Boom. That one, when you solve it, it'll be of degree 4 if you actually multiplied everything out. But also if you solve it, these are the only real roots. 1, 2, and 3. And boom, that's an example of an open-ended version. I really wanted to stretch the open-endedness of it. Two more questions. Number 47. Find the values of x in terms of y that are solutions of each equation. We have x plus y, part A, x plus y times, oh, I hate when my stylus does that. I really need to get a new one. X plus y times 2x minus y equals 0. So the concept of this just says set these equal to 0 and solve for x. Y is going to be in the answer, and that's totally fine. I mean, that's just, I'm not solving for y. Subtract y from both sides, x could equal negative y. Or if I add y to both sides and divide both sides by 2, x could equal y over 2. That's part A. Part B. Okay, when I'm looking at part B, it's looking a little bit like it expects us to know something about quadratics and such. I don't think you're expected to know how to factor a difference of two squares yet. So we will be talking about roots here. I think it's probably now worth me saying that if you took the square root of both sides, you get into rut row territory. If you take the fourth root of both sides, you get into rut row territory. So let's look at this part B. Either, and I'm running out of binder paper here as you can tell, either x squared minus y squared equals 0 or 4x plus 16y equals 0. Let's start with what would actually be the easier one. It's right here. 4x equals negative 16y, and you divide by 4, x equals negative 4y. That's one of your answers. On this one, I can add y squared over like this. And then I take the square root of both sides. That actually is what gets me to solve for x. Yeah, I guess in IM1 you did square roots. I'm just thinking that this book didn't really do it. And we're going to solve using square roots later. But you get here and you get x equals. Now, the square root of y squared, I don't know how they would end up putting this answer. I guess part of it is just saying y. But there's actually more than one answer. There's positive or negative y. In that case, and I wonder how deep they're going to get into that. That's a pretty tricky problem because remember, when you square positive y or negative y, you get the positive result back out, and I don't know what y represents, so I'm just going to go ahead and put it like that. Okay, and the last problem, this number 48, solve the equation 4 to the, yeah, I'm really curious how what stuff we need to know and not. Solve the equation 4 to the x minus 5 power minus 16 times 3, times 3. This is the last problem. Let me get to it, please. Times 3 to the x minus 81 equals 0. So same ish as before. Set these separately equal to 0. 4 to the x minus 5 minus 16 equals 0. If I add 16 to both sides, I get 4 to the x minus 5 equals 16. And, oh, sorry, let me set this one up. Or 3 to the x minus 81 equals 0. Let's actually, I started that one. Let's go to this one. Let's add 81 to both sides. 3 to the x equals 81. You know, it's going to be a little easier for a problem like this. And I already forget what we taught and didn't teach before. They're asking 3 to what power is 81 here. And I can tell you the answer is 4. And, you know, part of that thing is you really got to figure out what that would become on this side. 3 to the x equals 3 to the 4th. So x would equal 4. What value of x would get you that answer otherwise, right? But that's how this thing works as well. You're thinking of 16 really as 4 squared, right? 16 is 4 squared. And if I have the same base on both of these, I really want x minus 5 to become 2 because I want 4 squared to equal 4 squared. So what value for x minus 5 would get me 2? Add 5 to both sides, x would have to equal 7. And those are the values that would get me 0 as a result of this. It's a little different kind of problem because it uses exponentials and stresses it out that way. Okay, guys, so that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching, and I hope that this is making some sense when it comes to factoring, which is really the big key on this, and zero product property. In the future here, we're going to be looking, my camera really moved. In the future, we're really going to be looking at a lot more factoring in different detail. Greatest common factor is always a portion that you should be looking for, but on top of that, we're going to see what other kinds of factoring is in the way with quadratics so we can keep solving using zero product property. That'll do it for this one. This is Mr. Robinson. Thank you so much for watching. I think I already said that, and I will see you in the next one. Take